So as I said in a previous slide, in general, reaction rates depend on the concentration of reactants, although we will say that that's not always the case, but in general they do depend on the concentration of the reactants. And when you will only have one reactant, then that seems quite straightforward. It depends on the concentration of the reactants. But what happens when you have more than one reactant, 2, 3? Do they depend in the same way of all of them or not? And the answer is not necessarily. So we define something called rate laws, and rate laws are equations that you determine experimentally. So they are not generated, they are not models, they are experimentally derived equations from doing that reaction with different concentrations of different reagents until you work out how the rate of that particular reaction depend on that particular reagent. So if we have a generic reaction of you have a certain amount of compound A and compound B to give you compound C and B, the rate of reaction can be defined with this equation. Is K, which is what we call the rate constant, and we can talk about it in a second, and the concentration of each of the reagents to the power of a number. It's a small whole number. It can be 0, so that means it doesn't depend on the reagent. 1, 2, 3. That sort of numbers I'm talking about. And again, that's not something that you propose or calculate. That's something you determine experimentally by keeping one of the reagents constant and varying the quantity of the other reagent, and see if that affects the speed of the reaction. And if it does, how does it affect it? So K is a rate constant, and K is a constant which is related to the reaction, to those particular reagents, how easy it is for them to react. So it depends on the reaction, because it depends on the reagent that you're using, and it also depends on the temperature, because temperature can help speed reaction rate. So the same reagents at 20 degrees will react at a different rate that if those reagents are at 30, 40, or 50 degrees. So K encompasses the fact that you have those particular reagents that will react in a particular way, the fact that the reaction is happening at that particular temperature, so it's depending on the temperature, and also the presence of a catalyst. Are they only the reagents, or do you have an additional substance in the medium, the catalyst, that will help speed the reaction? So K, the rate constant for the same reaction, will change depending on the temperature of the reaction. Even if the reagents are the same, will change if the temperature changes, or if the reaction is performed in the presence of a catalyst. So how do we put all this together? The fact that you have reaction rates, how fast a reaction goes, that the reaction rates often depend on the concentration of the reagents, but when you have more than one reagent, they might not depend on the concentration of each reagent in the same way. How do you put all that together? Well, you classify reactions with respect to their order, and you talk about the reaction order of a reaction. And zero order is a reaction that has a constant rate, independent of the reagent's concentration. So it doesn't matter how much reagent you put, the reaction has a reaction rate, which depends on the temperature and the catalyst, but not on the concentration of the reaction. So if you think of those subscripts that we had before, and I told you, they can be small numbers, so you have K, and let's say that you have a very simple reaction, only the very simple one of one reagent to give you a product. So this is how you define a zero order reaction, because something to the power of 0 is 1, so that means the rate is constant. It doesn't matter how much reagent you add, the reaction will go at a particular rate, and that's it. First order, reaction rate doubles when the reactant is double. And what does it mean? It means that there is a direct relationship, a linear relationship between the concentration of the reagent and the rate. So you double the reaction, you double the concentration of the reagent, the rate doubles. You triple the concentration of the reagent, the rate triples. So it's a linear relationship, and that's what we call first order. Second order is when the rate quadruples when the amount of reagent is double. So you double the amount of reagent, but the reaction rate, because you have that to the power of 2, actually the speed is quadruple. So that's where the 0, first, second order refers to those small numbers, those coefficients I mentioned before. 0, that coefficient is 0, 1, first order is 1, and it's just different ways. Third order, you might kind of see where this is going. The rate increases 8 times when the reactant is double. So you have that cubic concentration of the reaction, the concentration of reagent to the cube, and I'm defining it with respect to one reagent. And if you had more than one reagent, you could define reaction rates with respect to each reagent, and you would have what is called an overall reaction rate, which would be adding up all those small superscripts. So for example, a reaction order, if you have a reaction that has 2 reagents and one is 0 order with respect to one reagent and first order with respect to the other, the overall reaction order would be 1. If you have a reaction against that has 2 reagents and is first order with respect to one reagent and first order with respect to the other reagent, the overall reaction order of that reaction would be 2. So you just add up those numbers. Okay, so how would I go about solving this exercise if I had this data? Let's have a look at the initial rates. Well, the first thing I can discard straight away is that the reaction is 0 order. It's not 0 order. If it were, the initial rate of the reaction would not change with the initial concentration of cisplatin. It doesn't matter. That's what 0 order means. The concentration of the reagent does not affect the speed of the reaction. The reaction rate is what it is, and it doesn't matter how much cisplatin you've got, the reaction rate will be constant. And that's clearly not the case. So as you can see, the reaction rate increases when you use more cisplatin. So the initial concentration of cisplatin is clearly affecting that initial reaction rate. So no 0 order. What would happen if this was a first order reaction? Well, in a first order reaction, the reaction rate will double when the concentration of the reagent doubles. So they are directly proportional. If it triples, it will triple. And if I look at the difference between these concentrations that work really well, like I can see that different concentration is always double. So the second concentration is double. The initial concentration in the first experiment is half of the second experiment. Or let's put it the other way around. It makes more sense. The concentration of cisplatin in the second experiment is double the one of the first experiment. The concentration of cisplatin in the third experiment is double than the second experiment. It doesn't work for the fourth one, but the first 3 already helped me. So the concentration of cisplatin in the first, second, and third experiment, they have, the researchers have doubled it. What has happened to the reaction rate? Well, hopefully you can see. If not, you can divide 1.8 10 to the minus 5 divided by 9 10 to the minus 6, or 3.6 10 to the minus 5 divided 1.8 10 to the minus 5. The reaction rate doubles. So when you double the concentration of cisplatin from one experiment compared to the next, the initial rate of the reaction will double. That means this reaction is first order. Okay, this exercise might be a bit tricky, because we're getting to very chemical, very chemical oriented in these videos. But I'm going to encourage you to stop the video and have a go at trying to predict what would be the reaction order of this particular reaction. Is the decomposition of cisplatin? It's a very common anti-cancer drug. Still, you know, one of the first ones that were ever designed and actually still used nowadays. And to be active in the body, it gets hydrolyzed first. So it reacts with water and produces, loses one of those chloride anions and incorporates a water molecule in the structure. So the question is asking you, what is the reaction order of that reaction? And it's giving you a series of experiments, 4 experiments, in which you have different concentrations of cisplatins and particular initial rates in molarity per minute. And the reaction is asking you what's the reaction order just with that value. So think about it. If this is a 0 order reaction, then the reaction will be independent of the concentration of the reagent. If it's a first order reaction, then the concentration of the product will double when the concentration of the reagent, the rate of the reaction will double when the concentration of the reagent doubles. And if it's a second order reaction, the rate of the reaction will quadruple when the concentration of the reagent doubles. So let's stop at 0, first or second order. So which is this reaction? Stop the video now, please.